Hi, welcome back to Mrs. Thompson's classroom. Today we're going to talk about exponential functions. So we're going to learn how to evaluate them, how to graph them, and then we're going to do some application problems with interest rates. So the first thing we need to know is, what is an exponential function? Well, it is a function in this form, a times b to the x. Okay, so notice the variable, the x, is in the exponent, hence the name. Okay, so if b is the base, let's investigate a few things. If b is 1, then I have a times 1 to the x, which is just a, so the function is constant. Okay, if b is less than 0, so let's just try out a few. Say it's a -1. Okay, then if I do -1 to the first, I'm going to get -a. But if I get a times -1 squared, I get +a. And then if I go back and do it cubed, then I'll get a negative again. And if I do it to the fourth, I get a positive again. And so the function is alternating. It's what we would call an oscillating function. And so this is not exponential, because it's not a continuous function, okay? And if b is 0, then I get a times 0 to the x. Well, that's just 0, so we have a constant function again. So there are some rules on what our base can be. We don't want it equal to 1, we don't want it equal to 0, and we don't want it negative. Okay, so notice here we want a base that is positive and not equal to 1. Okay, and the variable must be in the exponent. So this first one is, and its base is 2. The next one is not exponential because the base is less than 0. And the last one is not because the exponent is not the variable. In fact, in this one, this is a quadratic function, so it would graph a parabola. Okay. And now, how do we evaluate these? Well, we want to be able to use our calculator, because sometimes we're dealing with decimals. You know, we can do 2 squared and 2 to the 4th and even 3 to the 5th and things like this, but sometimes we have decimals. So we're going to use this little caret button right here on our calculator if you're using one of these graphing calculators, and you're literally going to type in 3.2 times 5.1, and then you'll type that caret 2.1 in order to get your answer. Okay, and then the same thing will go for this next one. Okay, so if I plug that into my calculator, let's see what we get. Get 97.9597, and it actually keeps going. Okay, and then to do this next one, we do 3.2 times 5.1, and we'll type that caret button, and we'll do the square root of 3. And we get 53.789. And again, it keeps going. Okay. So you're just going to type them in just like we see them and get this in the calculator. Now, how do we write functions that are exponential from a data set? It's not uncommon out in the real world, in jobs and in business and economics. We take data and we want to figure out a function that's going to model that data so we can make predictions. And so in this case, I'm told that it's an exponential. So I'm going to start by assuming f of x is a times b to the x. Okay, and then I'm going to take one of the data points. So if I use the point 0, 5, I'll get 5 equals a times b to the 0. Well, b to the 0 is 1, so this tells me what a is. A is actually called our initial condition because it is what happens, what the function is doing when x is 0. Okay? Now that I know that, I can take any other data point. So let's use the 110. And this will tell me 10 is 5 times b to the first. So dividing by 5, I'll get b equals 2. So my function becomes 5 times 2 to the x. Now, one other thing to note is sometimes you don't know the 0 condition, that initial condition. You can still use any 2 points and solve for a and b, set up a system of equations. The other thing to note is I notice when I look at these data points that each of the y values are a multiplier by 2. So that tells me that my b is 2. Okay, so anytime we have that common multiplier like that, it's forming an exponential, and that is my base. So even if I didn't know the 0 condition to get a, I can see what the b is, and then once I know b, it's easy to find the a. So now sometimes they just tell you we want a base and an initial condition, so this one just tells me that f of x is -2 times 4 to the x. Notice it is okay for the a to be negative. B cannot, but a can. Okay? All right, and what do these graphs look like? Well, to graph the first one, let's just plug in some points. So we're going to let f of x equal 2 to the x. So I'm going to go 2 to the -2, so that's going to become 1/4. The negative means I'm going to flip it over. 2 to the -1 will be a half. 2 to the 0 is 1. 2 to the first, and 2 squared. And then once I get those data points, I can plot each of those points, and I can connect the dots. Okay. Now notice an exponential is going to be greater than 0 because the base is greater than 0 for every value of x. So this function has to stay above the x-axis. But it does get smaller and smaller the more negative the x gets. So its domain is going to equal all reals, but its range is going to be bounded by that 0. Okay? All right, so let's write down some general characteristics of these functions. Okay? So first of all, the domain is always, as I said, all reals. The range is greater than 0. Not equal to, just greater than. They will always go through the point 0, a. A times b to the 0 is a times 1, which is a. Okay, so unless we are adding and subtracting something, they will go through that point. They will have a horizontal asymptote at y equals 0, unless we move the function up or down. If b is greater than 1, it is a growth function, which means it is increasing. Okay, and if b is between 0 and 1, then it is a decay. And so it is a decreasing function. Okay, so let's go back and look at what happens when I make b less than 1. So now taking 1/2 to the -2 is going to be like 2 squared, so that's 4. 1/2 to the -1 is 2. 1/2 to the 0 is 1. And I can keep going and get these points and plot each of them. And now you can see that the function decreases, but again, it's going to stay positive. So it's going to stay above the x-axis. And this is a decay because b is less than 1. Okay. All right, but the range is still all real. I mean, the range is above 0 and the domain is still all reals. Okay. All right, so let's graph another one. We notice here that this +1 is going to move it left 1 spot, and the -3 is going to move it down 3. Now, the interesting thing is moving it down 3, now my horizontal asymptote is at y equals 0 minus 3, which is -3. So I'm going to, before I even start graphing, I'm going to mark that line. Okay? We said they start by going through the point 0, a. Well, in this particular place, that would be the a is 1, right? So this goes through 0, 1. Then we move it left, and so that would be at -1, 1. And then we move it down 3, and so we get -1, -2. Move a point right here. Okay. Any other points, I can just pick and let x equal. So what happens if x equals 0? I'll get 2 to the 0 plus 1 minus 3. So that's 2 minus 3, that's -1. So it's going to connect through these two down towards the asymptote and up forever and ever. And you can get more points for more precision. So if x is 1, I'll get 2 to the 2 squared minus 3, which is 1. So it should hit this point right here. Okay. 2 or 3 points will make a nice, precise graph, but also mark that horizontal asymptote. But notice all the rules for our translations and transformations are still working the same. Nothing changed because it's an exponential function. Okay, so that's enough for that. Next time we're going to talk about a very special exponential function called the natural exponential, or just the exponential function. So I will see you then. Hopefully that helped, and be sure to comment below if you've got questions.